Today we'll be presenting our project on retinal disease classification using deep learning. I'm joined by Harsh and Yash, and we're excited to walk you through our approach to improving early eye disease detection using machine learning models. Just a second. Yeah, so retinal disease like diabetic retinopathy, cataracts, and glaucoma are some of the leading causes of blindness worldwide. Unfortunately, these conditions often progress silently until vision is permanently damaged. This makes early detection absolutely crucial. Our project aims to tackle this by developing a robust deep learning model that can classify these diseases from retinal images, ultimately supporting faster, more accurate diagnosis. So for this purpose, we use the retinal fundus multi-disease image dataset. It includes four key categories: normal, cataract, glaucoma, and diabetic retinopathy. These are all conditions with significant impacts on our vision, and accurate classification can dramatically improve outcomes through early intervention. So the dataset consists of 4,270 fundus images evenly distributed across four classes: cataract, diabetic retinopathy, glaucoma, and the normal case. This balanced distribution is especially important for training a fair and generalizable model that doesn't favor one condition over others. So understanding the dataset is just the first step. Now we'll look at how we prepared and structured the data, starting with the input and output formats, moving into pre-processing techniques.
The input and output, IDs retinal images are input. Each of these images has a label from one of these four classes, that is normal, cataract, retinopathy, or glaucoma. These are the pre-processing techniques that were used by us. Normalization, data augmentation, the images were resized for neural network architecture compatibility. Dataset was split into three categories, that is training, test, and validation. The output is predicted label with respective class associated confidence score for each prediction. Performance metrics like accuracy, precision, recall, and F1 score are also part of the output. Talking about the visual comparison, this is a comparison where there is a grid view of images with predicted label, confidence score, and actual labels. Now, talking about data pre-processing, to prepare dataset was split into 60% training, 20% validation, and 20% testing using stratified sampling to maintain class distribution. Talking about the steps of this pre-processing, images were loaded using the PIL library first, then they were resized to a consistent shape for the model input. Images were converted to numerical arrays and were normalized to scale pixel values. Label encoding was applied to convert the class names into integers for model compatibility. Data augmentation techniques such as random flips, rotations, or brightness adjustments were used for better generalization and to reduce overfitting. Talking about the class balance check, we verified distribution of classes across splits to ensure balanced training, validation, and test datasets. Talking about the baseline model architecture, a custom convolutional neural network was used to classify these retinal fundus images into four categories. This is the architecture of the baseline model, where the input are images of shape 224 by 224, and these are RGB images. Talking about the architecture, first of all, we started with four different convolutional layers. Each uses a 3x3 kernel, followed by value activation, then base normalization, and max pooling. Now, first layer starts with 32 filters, then 64 filters, then 128 filters, and then finally 256 filters. After this, the output was then flattened, and it was passed to these fully connected layers. Two fully connected layers were used. First was used with 256 neurons, followed by dropout regularization, and the second one was with 128 neurons, followed by again value and dropout regularization. In the finally, for output, softmax activation was used for the multi-class classification, and the optimizer used was Adam optimizer with a learning rate of 0.0001. We used the categorical cross entropy loss function, and regularization techniques such as dropout and best normalization were used. Again, as I mentioned earlier, data augmentation techniques like rotation, shift, zoom, and flips were used, and early stopping and reduce alarm collective were used. Now, these were the results of our baseline model. So this is a confusion matrix you can see here. These are the actual labels, and these are the predicted labels. Talking about the data set performance, 69% accuracy was observed on unseen data, and a micro average score, F1 score of 0.69 was observed. Total data samples were 844. And these are the two graphs comparing training and validation accuracy, and then training and validation loss.
You can see over here, this is the architecture of our custom model. It takes an input of image size 256 times 256 times 3 for RGB format. The overall architecture overview, as you can see from over here, is that it uses three blocks having convolutional layers with different size, with different number of filters and different kernel sizes, using same value activation function and same padding, followed by max pooling layer and the best normalization layer. However, the block 4 uses the separable conv 2D layers with 512 filters for reduced parameter count and efficient learning. It also uses max pooling and best normalization layer, followed by the convolutional layer. Then all the filters are then squeezed into a single dimension, and then a global average pooling is applied over them, followed by two dense layers with different number of units and value activation function. We had used dropout to prevent overfitting, obviously. And for the output layer, it has 4 neurons for 4 different classes. Now, moving on to the loss and accuracy graphs. So as you can see from over here, the training and validation loss decrease steadily, while the accuracy improves consistently across each epoch. And there is a minimal gap between the training and validation accuracy around after epoch 60. And we had used early stopping for our training purposes to prevent overfitting. And as you can see from the graph, that the minimal gap between the both of these accuracies, it indicates good learning and control overfitting. Now moving on to the matrix. So as you can see from over here, The metrics for our custom model is much more better than the one that we had in the baseline model. And this is the classification report for our custom model, which achieved a weighted average of 0.88 precision score, 0.88 recall, and 0.88 F1 score as well. The best performing class was the diabetic retinopathy class, which had 0.99 precision. Now, evaluating the model. So the model achieved an accuracy of 88% on the test data set, and the accuracy curve shows the consistent learning with the gradual improvement across each epochs. The training loss also steadily decreased across as the number of epochs increased. And from the evaluation metrics, as I said before, the diabetic retinopathy class achieved the highest precision score of 0.99 and highest recall score of 0.99. The classification report also confirms the effective minimization of both the false positives and false negatives in our case. Now, this slide contains the previous work experiences of all of us. So we have experience working with computer vision projects with CNN models and working on the medical image datasets as well. And these are the references. So our dataset was obtained from the Kaggle. This is the link for that dataset. And these are the two research papers which we have used